Imagine you're decoding an alien language with only a list of sorted words. Can you reconstruct the whole alphabet? Alien Dictionary is a Pattern Mastery 100 Super Challenge. Regularly asked at Google, Meta, and Amazon to test your grasp of graph theory, topological sorting, and string manipulation. Over 40% of candidates either miss edge cases or get tangled in cycle detection. Master this, and you'll shine on advanced ordering problems. Let's break down Alien Dictionary using the basic method, giving you a foolproof plan for any graph-based string ordering challenge. Given a list of words sorted according to an unknown alphabet, return a string representing the alphabet's order. If no valid order exists, cycle, return. List of words, all lowercase letters, possibly with overlaps and missing letters, a string of characters, the alien alphabet order, or if invalid. Suppose you're designing a search tool for a new language, or analyzing a secret code with custom rules. An interviewer might ask, how would you deduce task dependencies from log order, or infer a dictionary structure from partial data? What's tricky? You need to infer order constraints between letters by comparing adjacent words. Must detect cycles. If two letters are required to come before each other, there's no valid order. Not all letters may be present in the input, and some may be missing from certain orderings. Build a graph. Each unique letter is a node. For every pair of adjacent words, find the first position where they differ. That's a precedence constraint. Edge, topological sort. Apply Kahn's algorithm, BFS, or DFS to produce a valid order. Use an indegree map to track how many incoming edges each node has. Add nodes with 0 in degree to the result. Decrease in degree as edges are used. Cycle detection. If at the end, you haven't used all letters, result is shorter than unique letters, there's a cycle. Let's clarify. If a word is a prefix of another but comes later, it's invalid. For example, ABC, AB. All letters in words must appear in the output. Edge cases. Empty word list. Return. Words with same prefix. Skip until the first difference. Cycle in constraints. Return. Initialize a graph, adjacency list, and in degree dictionary for all unique letters. Compare each pair of adjacent words. For each character, find the first mismatch. Add an edge from char1 to char2. Char1 comes before char2. If one word is a prefix of the other and is longer, return. Topological sort. Add all nodes with 0 in degree to a queue, while queue isn't empty. Pop from queue, append to result. Decrease in degree for neighbors. If in degree becomes 0, add to queue. If result length equals the number of unique letters, return as a string. Otherwise, return, cycle or invalid input. Let's try to implement it using solution 1. Time complexity, OV plus E. The concept discussion. We're given words already sorted in an alien language, and we need to figure out the letter order. The key idea is to build a graph of letter rules. If letter A must come before B, we add an edge of B. We discover these rules by comparing each adjacent pair of words and finding the first position where they differ. That first mismatch tells us the ordering rule. After we build all rules, we run topological sorting, Kahn's algorithm, to produce a valid letter order. If we detect an invalid case, like a longer word coming before its exact prefix, or we can't include all letters, cycle, we return an empty string. This function builds a letter graph from the word list, then uses topological sorting to return a valid character order, or an empty string if it's impossible. First, we gather every unique character that appears anywhere in the input. Even if a letter doesn't have any rules pointing to or from it, it still needs to show up in the final answer. We set up adjective as a graph that stores what each letter must come before. Indegree to count how many rules are pointing into each letter, basically how many prerequisites that letter still has before it can be placed. Now we build the rules by looking at words two at a time, because the list is already sorted in alien order. We compare W1 and W2, and the first character position where they differ tells us the rule, W1J must come before W2J. That's the only rule we need from that pair, so we stop comparing after that first mismatch. Now we start topological sorting. Any letter with indegree 0 has no prerequisites, meaning it can safely appear next in the order. We push all such letters into a queue to begin processing. This loop builds the final character order. We repeatedly take a letter from the queue, add it to the output, and then remove its outgoing rules by decreasing the indegree of its neighbors. If any neighbor drops to indegree 0, it becomes ready, so it joins the queue. This continues until no more letters can be placed. At the end, we check if we successfully placed all characters. If yes, we join them into a string and return it. If not, it means a cycle or contradiction prevented some letters from ever reaching indegree 0, so we return an empty string. And that's how this algorithm works. It first collects all letters and builds a dependency graph by comparing adjacent words for the first mismatch, then it topologically sorts the letters with a queue by repeatedly taking zero-indegree characters and unlocking the next ones, until it either forms a full valid order, or detects an impossible cycle. Efficient, simple, and elegant. Let's test our function using this input list of words: WRT, WRF, ET, RFTT. These are words already sorted in an alien language, and our job is to figure out a valid character order that makes this sorting possible. First, the code collects every unique character it sees and sets up an in-degree map, how many prerequisites a letter has, and an adjacency list, which letters must come after another. Then we compare each pair of neighboring words to find the first character where they differ. That's where we learn a rule. Let's walk through the key comparisons. WRT versus WRF, first difference is T versus F, so TF. WRF versus first difference is W versus E, so WE. Versus ET, first difference is R versus T, so RT. ET versus RFTT, first difference is E versus R, so ER. So we've built a chain of dependencies that basically forces WERTF. After that, we run a BFS topological sort. Start with letters that have in-degree 0, no prerequisites. Pop them into the result, and decrease indegrees of their neighbors. And the final output is WERT, exactly matching the expected answer. That output makes perfect sense because it satisfies every rule we discovered from the sorted word list. W comes before E before R before T, and T before F. So, our implementation is correct. The algorithm successfully reconstructs the alien alphabet using graph constraints and topological sorting, efficient and accurate. Let's try to implement it using solution 2. Time complexity, OV plus E. The concept discussion. This DFS-based solution still builds a graph of letter rules, but instead of using a queue, Kahn's algorithm, it uses DFS topological sorting. We compare neighboring words to find the first differing character, and that gives us a must-come-before rule like a B. After building the graph, we run DFS across all characters. We track each character's visit state: unvisited, visiting, currently in the recursion path, and visited, fully done. If we ever revisit a visiting character, that means there's a cycle, so the order is impossible. Otherwise, we add characters to an output list after exploring their neighbors, then reverse at the end to get the correct order. This function creates a dependency graph between letters, then uses DFS with cycle detection to build a topological ordering, or returns an empty string if it's impossible. First, we collect every unique character that appears in the word list. That ensures our final answer includes letters even if they don't participate in any rule. Then we create an adjacency list entry for each character, basically a place to store what letters must come after this one. Next, we build the graph rules by walking through word pairs. Since the words are already sorted in alien order, we only need to find the first mismatch between each consecutive pair. That mismatch gives a direct ordering rule. The character from the first word must come before the character from the second word. Now we prepare for DFS. We track each character's state. 0 means unvisited. 1 means visiting, currently in the DFS path. 2 means visited, fully processed. We also keep an order list to build the final answer, and a valid flag that flips to false if we detect a cycle. See, this DFS does two jobs at once. Cycle detection. If we ever enter a character that's already marked as visiting, that means we looped back into the current recursion path, so the graph has a cycle and the ordering is impossible. Build ordering. We add a character to order only after exploring all of its neighbors. That add later behavior naturally creates a topological ordering. We run DFS starting from every character that hasn't been visited yet. This matters because the graph might not be one connected piece. There may be separate groups of letters with no relationship to each other. If any DFS run detects a cycle, we stop and return an empty string. Because we pushed characters after finishing their neighbors, order is built in reverse topological order. So we reverse it at the end to get the correct alien alphabet order as a string. And that's how this algorithm works. It first collects all characters and builds a dependency graph from the first mismatches in adjacent words. Then it runs DFS with cycle detection and post-order stacking to produce a topological order, reversing at the end to return the final alien alphabet string. Efficient, simple, and elegant. Let's test our function using this input. Z, X. These are words already sorted in an alien dictionary, so the order tells us something about how the alien alphabet is arranged. First, the code gathers every unique character from all words. Here that's just Z, X. Then it compares adjacent words to build ordering rules. We compare Z and X. The first characters differ immediately. Z versus X, so we learn the rule, ZX, meaning Z must come before X in the alien alphabet. After building the graph, this solution uses DFS topological sorting with states. 0 equals unvisited. 1 equals visiting, currently in recursion. If we see this again, it's a cycle. 2 equals visited, fully processed. We DFS from each character. When DFS finishes a letter, we push it into order, then we reverse order at the end to get the correct topological order. Since there's no cycle here and the only dependency is Z before X, the final ordering comes out cleanly. And that's exactly what our program outputs, ZX, matching the expected result. That output makes perfect sense because the sorted input words force Z to appear before X, and our DFS-based ordering respects that. So, our implementation is correct. The algorithm successfully builds character precedence rules and produces a valid alien alphabet using DFS topological sorting, efficient and accurate. Alright, quick recap to wrap up Alien Dictionary. Conceptually, we're given a list of words that are already sorted, but in an unknown alphabet. Each unique letter becomes a node in a graph, and we compare adjacent words to figure out ordering rules. The first place two words differ tells us the key constraint. One letter must come before the other, which becomes a directed edge in the graph. The core idea is that this isn't really a language problem, it's an ordering constraints problem. A valid alphabet order only exists if those constraints don't create a cycle. That's why topological sort is the right tool. It builds a valid ordering when possible. We also have to watch for tricky cases like prefix conflicts and letters that appear but don't connect to anything. Those still need to be included. The plan was, first, initialize the graph using all unique letters across all words. Then compare each adjacent pair of words and add a directed edge based on the first mismatch. Track an in-degree count for each letter. Finally, run topological sorting by starting with all letters that have in-degree 0 and building the order from there. We built the adjacency and in-degree structures carefully, avoided duplicate edges, checked the invalid prefix case early and returned empty immediately when needed, then ran a standard topological sort approach. The solution ran cleanly on LeetCode with no errors. We confirmed it behaves correctly on valid dictionaries, returns an empty result when a cycle makes ordering impossible, and also returns empty for the invalid prefix scenario. And of course, all test cases passed. The key takeaway is, turn sorted words into graph edges, then let topological sort reveal the hidden alphabet. And cycle detection is the ultimate truth test. Master this pattern, and a lot of ordering problems become straightforward.